Welcome to the 70th video in our series about Unix tools. In this video, I'll show you how to create a static library and use it. The demo program computes the sine of x, where x is an angle in radians, using a Taylor series and compares it to the system's implementation of sine from libm. There is a lot of material to cover. The basic structure is shown here. This is a dependency graph. Tested is the application. It depends on tested.o and libmylib.a, etc. Pause the video and soak that into your brain. Now, are you back? Great. Compiling each file to create the objects is the same as in video 69 using the -c option. Creating the static library uses the Unix AR and ranlib tools. A static library is basically an organized and indexed, after you run ranlib, collection of object files for the linker to use. We won't worry too much about details, but basically you can use a sequence like this. AR, R, your static library name, and a list of one or more object files. After you've updated your archive, run ranlib to update the index. You can update or add an object file later by just running the same command again and listing the file you want to update or add. And you may wonder, how do I use this static library? The simplest way is like this. Just add it on the compile line where you're linking in the same place the object files would be. But normally we don't do that. Normally we do something like this. We give a -big L and then the path to where the library is. And today we'll be using dot because it's in the current directory. And then you do -L lib whatever. Fix that. -L whatever. It needs to have a lib on the name, but when you use the -L, it assumes there's a lib, and it chops the lib, and it chops the .a, and then it uses this part. So why would you use a static library? It avoids having to type a long list of object files when you link, and the linker is smart, and it will only use the object files it needs, and it will copy the routines that you actually use into your executable. And wow, I have a lot of typos. Sorry about that. And the routines you don't use don't get copied. Okay, let's do it. Here you can see that I've got the factorial header file with the appropriate prototype, and in the bottom window you can see the actual implementation. That was for factorial. This is for the actual Taylor sine, which uses factorial. Again, in the upper window you see the header file that has the prototype, and in the bottom window you can see the actual implementation. And finally, we have the test routine that includes the Taylor sine. And what it does is it calls our Taylor sine, then it calls the real sine from the libm library. It computes the absolute value of the difference of the two values and makes sure it's less than a tolerance. And if it is, we pass. If it's not, we fail. Okay. And before you ask, yes, this is VIM that I'm using. And we'll have a video later to show you how to set this up. But let's get to it. If we look at our files, we need to compile factorial. We need to compile Taylor sine. And those are the two object files that we need to put in our archive. So Don't forget you have to have that lib prefix, then whatever name you want, and then an A. And then you list the object files that you want to be inside it. Finally, you run ranlib to add that special index. We need to compile our test it. And now we're ready for the link. So we'll GCC, whatever object file has the main, any other object files that are not in the archive, we don't have any. And then we need to say where we're going to put the output. It's going to be called test it. And we need to -L to say where do I look for the archive, and we put a dot because we want to look in this directory. And then we say L, and we don't say lib, and we don't say .a. Finally, I have to do an LM. The LM is so we can use the system version of sign because it's from the math library. And when we hit enter, we should have a valid link. And when we run it, you'll see we passed the test. This is the Taylor sign. This is our input, which is pi/4. And we get this answer. We call the system sign with the same input, and we get this answer. They're not exactly the same. We take the difference of those two answers, but it might be negative, so we take the absolute value, and we get this number. And this shows how accurate we are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We're good to 15 places, which is pretty good. And so we've managed to create the archive and use it. And what would happen if we change something? Let's go into the factorial and make a change. And so here it is. We say an inefficient, and we should really say recursive because this is using a recursive algorithm instead of a loop like it should. And we save it. So after I've changed that, I need to recompile it. We know that. What do I do next? Well, I need to go to the archive, but I don't have to list everything, just the one that changed. The rest of them will be left alone. I need to do another ranlib to rebuild the index, and then I can do my compile. That's really just a link. Test it didn't change, I don't have to recompile that. And Taylor's sign didn't change, I don't have to rebuild that. And if I run test it, you can see it works. So static libraries are great. They're not popular today for two reasons. One, glibc people hate it, so they make it a second-class citizen. And the other reason is, if you look at the size of tested, it's pretty large. And the reason why is, when you use these static libraries, the code gets copied. Only the code you need, but you still copy code into here. And it's in the executable. So anytime you need to update a file, like we updated factorial, you have to rebuild the archive and you have to relink every application that uses the archive. That's the downside. The upside is nobody can delete your shared object and break your program because it's in the executable. They can't take it away from you. That's what I wanted to show you in this video, and we have reached our time limit. I hope you come back next time. I'm going to show you the make file just for a sneak preview. You see there are no .os. And we need to remove the archive. And there's nothing there. And now if I type make, it creates everything. And you notice I've put in all kinds of options, and I've created a static executable. This means that even if they destroy libc, it'll still run, and you can see how much bigger it is when we do static. But it runs, it gives the same answer, it works great. So come back to video number 71 next time, and I'll show you the secret sauce inside that make file. But until then, thank you for listening.